So to begin to derive acceleration, we want to look back at fluid velocity. So in the last video, we saw that fluid velocity generally has three components: x velocity, a y velocity, and a z velocity. And those can be functions of x, y, and z and t, space and time, essentially. So in general, have a fairly complicated version of velocity. To derive the equation of acceleration, I want to make it a little simpler on ourselves. So basically take my three spatial dimensions, x, y, and z, and kind of replace them with only one spatial dimension, being the direction of flow, so whichever way the fluid's going. I'm going to call that s. So s ends up being what we call a streamline coordinate. If I have a fluid that's falling along this path line, or the streamline, I look at it, I have some location that I call s equals 0, and then s is just whatever the distance is along this line. Slight complication with that is that I have this new unit vector, so instead of going in the x, the y, and a z direction, I, j, and k, I have this one unit vector et, which is going to change in time. So over here, et is pointing this way, then it's pointing that way, pointing that way. So my life is somewhat easier in the sense that I only have one spatial dimension, s, as opposed to three. But as we're going to see a little later, the fact that et changes in time is going to make it a little more difficult. So in addition to my tangential vector, the direction of the velocity actually going, I also have a direction perpendicular to that, the normal direction. So En is going to be the unit vector associated with that. I'm pointing to the center of the circle, a center of curvature. Then instead, my velocity v is in this et direction, so my velocity v, same direction as et. And then I have this local radius r to wherever the center of the circle is. Then my acceleration, I could have two components. I could have at in the tangential direction, that's essentially speeding up or slowing down. And then I have an in the en direction, and that's essentially changing direction. So if we saw acceleration is a tangential component and a normal component, I basically want to now derive what at and an should be. So standard definition of acceleration is the derivative of velocity with respect to time. Notice this is a full derivative. That's very important. So I want to take the full derivative of my velocity v in the et direction. Now again here, both of these are functions of time. So I have a product rule. I take the derivative of the first one times the second one, and then the first one times the derivative of the second one. I'm going to look at these independently. So first look at this term here. The full derivative of velocity, which is a function of space and time, but this space is also a function of time. So when I take that full derivative, I get two terms. I get the partial v with respect to t, and then the fact that this s is a function of time gives me dv ds, ds dt. And then ds dt, s is my distance along my streamline, so some distance over some time, that's my velocity. So ds dt is just velocity. So this first term ends up being partial v partial t plus v partial s. So now moving on to the second term, the term involving the derivative of the unit vector. A bit more complicated, need some geometry here. So I have et at a certain time t equals 0 is in that direction. At a later time it's over there. So as my velocity particle moves, this et changes. It changes by that amount. So this is my first et, that's my second et, that's my delta et, that's basically what I'm looking for. So I want to compare this triangle to that triangle. So I kind of reorient this triangle. So I have this distance here is v dt. I have those distances of r, and then this is the same angle. So these are the same triangles. So I can basically make a ratio. Et over this length is the same as v dt over r. These lengths are the magnitude of a unit vector. Unit vector has length of 1. So et over that length is v dt over r. This is just 1. So delta et is v dt over r. That's my delta et. Now my derivative is basically delta et over delta t. And if I look at what I have over here, I have v dt over r. So take that, divide it by dt. All I'm left with is v over r. So my derivative is v over r in terms of magnitude. And then the direction, we can see just from this picture that the change in these two is basically straight down. straight down is my normal direction, and so this derivative of my unit vector is v over r in the normal direction. And now plugging this result in the previous one into my equation for my acceleration. The previous one I have dv dt v dv ds in the tangential direction, so that's from the last one. And then here I have a v times this guy, so I have v squared over r in the normal direction. And you might recognize that as normal centripetal acceleration. You've seen that guy before. So again, good news of all that derivation is we get the answer we expected. Centripetal acceleration there. In terms of the first guy, there's two terms. They both have special names. dv dt is called the local acceleration. v dv ds is called the convective acceleration. So my local acceleration is based on what's actually happening in time, is the acceleration here at this particular point changing in time. This guy comes from the fact that I've moved, so my particle has moved from this point to that point, and that point might have a different acceleration than the first point. So this is basically the fact that I'm moving to a different point which could have a different acceleration. So that's my acceleration. Total acceleration is the sum of all three. So example, I have water flowing through a curved hose. Radius of curvature at this point is 20 feet. Has an increasing speed of v equals 10 times t. That's in feet per second. And then 2 seconds later, I want to find the local, convective, centripetal, and total accelerations for this scenario. So my three components, local, convective, and centripetal. Local part of the acceleration is partial v, partial t. That's in the et direction. So v is 10 times t, so partial v, partial t, take that derivative, gives me just a 10. And then in terms of et, I need to look at my diagram, see which way I'm actually going here. Velocity going to the right, that's in the x direction, so et is I. So in terms of local acceleration, I have 10 in the I direction. For the convective part of that, I have v, partial s, also in the et direction. Now this guy, because I related this to x, y, and z coordinates, I can take my streamwise coordinate s and relate it to x and y and z. So again, looking at which way this thing's actually going, my streamline here at this particular point is going straight to the right. So straight to the right means that s is the same thing as x. So what I'm really looking for in this case is v dv dx, and again, et is in the I direction. And so now I'm taking my v, 10 times t, d by dx of my v, which is also 10 times t, in the I direction, partial with respect to x of 10 times t. There's no x here, so no x here means 0. So 0 convective acceleration in this case. And then finally my centripetal acceleration, v squared over r in the normal direction, 10 times t squared. Radius was 20 feet. And then again, my normal direction, you need to look at my figure. This is my tangential direction. Normal points towards the center of the circle. So center of the circle is straight down. Straight down is the negative y or negative j direction. So I have 100 t squared over 20 in the minus j direction, or minus 5 t squared in the j direction. And last thing I want to do is, it was specifically asking for the time at t equals 2 seconds. So my local was 10I, that's constant, doesn't change in time, so that stays as 10I. Same thing for my convective, still 0. But my centripetal acceleration depended on time. Just want to stick 2 in there for my t. So minus 5 times t squared gives a grand total of minus 20j. So those are my accelerations at time t equals 2. Then of course also want to be total acceleration. Total, just add these three together. Add them together gives me 10I minus 20j. And that of course is in feet per second squared, as all of them are in feet per second squared.